Good morning. So hope I am audible. Yeah, 1 minute just. Good morning. Good morning. Okay. So today we'll be learning okay, as we yesterday learned the absolute encoder, that is the absolute SSI encoder. Already we have learned yesterday, because this encoder is nowadays it's a very important optical sensor for position and velocity and RPM measurement. So basically the construction of the encoder, the mechanical construction of the encoder is very simple, but it is precise. High precision machining is involved. So here this black colors is denoted as hole. It is means this is this area. These areas are scooped out from a disc. Okay, so now you see, if the front side of the encoder, in the middle of each track, suppose I am putting some LED, and on the other side I am putting one photo detector. It is properly focused. That LED will be perfectly focused to the photo detector. Now what will happen if that disc is rotating? So say it is in this position. So through this black color, this will, so this, say this is the MSB and this is the LSB. Now for this particular position, that photo detector will detect the LED, because these areas are empty. So what we will get? 1 1 1 0 1 1 1 0. You got a bit sequence. So here it is 1 2 3 4 5 6 7 8 bit. Similarly, if that is coming in different position, say it is coming here, this position, when it is rotate and this line is come here, so you will get 0 0 0 1 1 1 0. So you will each and every position you will get a bit sequence. So that bit only it is transmitted through SSI protocol, and we are able to read that data. This was basically inside the absolute encoder. It is very much important to get the angular position. Directly it will give the angular position. SSI is used for a better communication purpose, mainly for long distance communication and error free communication. But still you can, each bit you can transmit through 8 wires, you can transmit using parallel transmission. You can transmit also directly, you read the bit, that is also possible, but that is long distance is not advisable, and number of wires required, transmission line number of cores required more. These are the advantage and disadvantage. Okay, now coming to the incremental encoder. In incremental encoder it is still much more simpler. So here these things, it is like this kind of holes are there, and one side that is the LED, another side the photodetector. Now if the disc rotate, you will get this type of waveform, pulse, on off on off on off, like that you will get. So basically you are mapping the rotation, and as quicker, as more speed that disc will rotate, this waveform will shrink. This means the frequency will increase. From that we can count the RPM. If we know how many these holes are there in the disc, then by counting one rotation, that is called PPR, pulse per rotation or revolution. So if this disc having some 100 PPR, suppose, so once like 100 pulses I obtained, once I obtained 100 pulses after something like this, then say here, then I will understand one rotation is completed. And if I able to measure this time, say I am storing that revolution, means the pulse, in a variable called n. Now if I divide it by 100, then means this variable will give one rotation. And if I able to get the time, so this is the t second, so this divided by t, so it is rotation per second. You multiply by 60, you will get rotation per minute, RPM. Okay, now I will show, say now I want to get some direction, whether which direction it is. So let us show you one small video. So instead of, you see here there is a single there is a outermost periphery, there is a single truck. If there is another truck and it is aparted by this, the next truck, that means what I am telling, that track, the bottom track will be, the hole will be in between these two. Okay, so that means when the pulse will be generated, both the pulse will be 90 degree aparted. How it is, let us see. It's a 1 minute video, just see.
so-called shaft encoder that generates a sequence of pulses.
You see, this is
serves as senders. A light-emitting diode serves as sender, and its light is detected by a photodetector. Therefore, the emitting diodes serve transparent sections that are equally spaced. A light-emitting diode serves as sender, and its light is detected by a photodetector. Therefore, the encoder can generate a sequence of pulses. The output is measured in pulses per revolution, which can be used to determine either the position or the rotational speed. To detect the rotational sense, the encoder needs two tracks. The sense of rotation determines which signal coming from track A or track B is leading. Here, you can see the signal form coming from clockwise rotation. To have a comparison, you see now the signal form coming from counterclockwise rotation. Now the signal coming from track B is leading. It is now up to the electronics to evaluate the...
You see, if the rotation change, the first when it was clockwise rotation, then the pulse A is leading. Now here pulse B is leading.
Signals.
So
also
this quadrature pulse is why? Because we need to know the direction of rotation also. So for that reason, this another track is made here, and that track will be in between of these two. Not exactly similar, it will be in between, so that it will be 90-degree aparted. Another pulse will come here like this. Now you see the same way. If you recall the video, so the sequence, this is for the outermost track and this is the inner track. So first is 1 1, both are high. Next is 1 0, next is 0 0, next is 0 1, and similarly the same state will repeat. Now if it is going from state 1 to 2 or 2 to 3 or 3 to 4, if it is happening, that means the disk is rotating like this direction. Now if you get first 0 1 sequence, that means fourth state and then third state, or first third state then second state, or first second state then first state, then the disk is rotating in the opposite direction. Very simple concept. So we have to map it. When we will be counting it, we need to map, we need to do the same thing. Okay, now you see I am making one truth table. So this is my past state and this is my present state. Now you see, if my present state is 1, sorry, if my past state is 1 and present state is 2, then it is going like this. That means the pulse should increase. It is rotating clockwise direction. So this is my first state and this is my second state. You see, if this things is happening, then I have to increment the number, pulse number. Okay, then you can see here, if my past state is 1 and if it is going this, that means if my past state is 1 and present state is 4, then disk is rotating in this direction. So I have to decrement. So you see, this is my present past state and present state, if it is 4, then I am decrementing. You can take another example. If my past state is 2 and present state is 3, it is going like this, then I have to increment. So you see, my past state is 2 and present state is 3. so I am incrementing. And if my present past state is 2 and present state is 1, that means here, then it should decrement. So you see, this is my past state is 2 and present state is 1. I am decrementing this. So all the 4 conditions I am mapping here. I am mapping here, and other area I am keeping as don't care. These are the don't care conditions. Okay, so I have made the complete truth table. So we will use this truth table to calculate the RPM. Let us see how it is. You see, these are the part, all these things I am not doing. So here I have not taught you, even though here I am using library function to, because very quickly I have to do, that's why I am showing you. Otherwise in the basics of microcontroller I will teach you what is external hardware interrupt. So there is a pin, external hardware interrupt pin is there in every microcontroller. You see here INT 0, this PD2 and INT 1. That means the pin number 2 and 3. Those are the external hardware interrupt. So if you see, I have used this 2 and 3 as interrupt. Okay. So pin number 2 is interrupt 0, pin number 3 is interrupt 1. So that's why I given this one. And I am using one service routine called channel A change and B change. And type of interrupt I am using, type of interrupt means whether it is rising edge or falling edge or any change or always high, low, all these things are there. So I am using any change is there. Okay. Now I am reading the state of these 2 pin. Now in the setup, that means in I am initializing the first. So you see, if it is both are 1, then is the state 1. You see, I am defining here. If both are high, my past state is 1. If both are one is high, another low, it is state 2. If it is low low, state 3. If it is low high, state 4. This is my past state. And I am using one counter that I am counting the time in microsecond. And here again I am counting, and I am taking the difference, which is called the time elapsed. So here you see count time I have used 1. This is 1 second, means 10 to the power 6. So it will be in microsecond. So if that is there, then I am calculating. This is my multiplying factor, because based on my PPR and all these things, sometimes you have to do that. So that's why I have kept it. And whatever the count I am obtaining, I am dividing by the PPR by 2, because pulse means first raising, then falling, then again raising. So you have to divide by 2, and that is my RPM. And after calculating, I am swapping this time present and time past. Continuously it is counting, and I am making the count as 0. Now I am coming to the interrupt service routine. In interrupt service routine, again I am reading that, and same I am, once this it is elapsed, some time is elapsed, means when that interrupt will occur. You see, in the interrupt sense, I have mentioned that change. If it is high to low or low to high, anything, it will come to this service routine. So when coming this to service routine, again I am reading the state. So if the present state, same high, it is present state 1, high low present state 2, low present state 3, and low high present state 4. Now I am using a switch case. So the present state. Now you see, if the past state, if the present state 1 and past state 2, you see here now, if the present state 1 and past state 2, I have to do the decrement. You see, I have used count minus. If the present state 1 and past state 4, this is the present state 1 and past state 4, I have to increment. You see, I have incremented. If my present state 2 and past state 1, I have to increment. You see, I have incremented. If my present state 2 and past state 3, I have to decrement. You see, I have decremented. Similarly, all the other state I have done, and after doing that, I am swapping the present and past state. Means again it will start to do the same thing. This is for channel A, and channel B also the same thing I wrote. Now if you burn this code and connect one incremental encoder with the controller, and if you rotate it, it will give you the RPM, or you can able to count the pulse. This technique is called quadrature pulse counting. So if you rotate clockwise direction, it will give positive RPM. If you rotate anti-clockwise direction, it will give negative RPM. This is the thing. So which is very much important in motor control, mainly in vector control, because you know, I have shown you the vector control, whatever I have shown you so far in the model, means in my simulation, those are sensor with sensor. That means the sensor is your incremental encoder or SSI encoder. But why we use the sensor? If you recall the governing equations, why we have used that sensors, this RPM sensor, to estimate the rotor flux. But there is another technique I have not shown you, that is called direct vector control or sensorless vector control, where by only sensing the current, I have shown you the technique to the sensor used to sense the current, that is LEM sensor. I think LA55 I have shown you what is the connection, how to connect it, how to set the measurement resistance, all these things I will show you. So you take the current, and from the current you can again estimate it. Still there will be some calculation you need not to understand in this course, because I framed in that way. So that is very important. Okay. Another thing I want to show you, I want to tell you, say here how many timers are there? How many timers are there? So this is one OC1, OC2, OC0. So there are 3 timers in this chip, and you know every timer will have the 2 channel. So normally people will use channel A for a non-inverting pulse and channel B for inverting pulse. But suppose I am working for a multi-level inverter where more pulses are required. That time if you do that, then only I can control 3 legs. But if I use only each channel for a distinct pulse, let complementary pulse generate with some delay and dead time, then I can control 6 legs. So always better to provide the generate the complementary pulse externally. It will much more safe, and through some external hardware circuit with dead time generation. So we need to know how the dead time should be generated. Normally how dead time is generated, if you see any driver, only one pulse you need to give, actual pulse you need to give, and the dead time setting will be in the driver card. So now we will learn how to generate the dead time. It's very simple. Say here I have used one pulse of 1 kilohertz. So say that is coming from your microcontroller timer output PWM. So you take that pulse, you use one AND gate, simple available, that is market available, one high speed AND gate, that it should not saturate in this frequency, at least that should be higher than that. Then here is a delay I have used. That delay you can use 555 timer, so many delay chips are available. Using that you can do that delay and set the delay here. So here I have used the delay I have used 2 millisecond or something like that I have used. That is my delay. Okay. Here also. So what I am doing, I am taking the actual pulse and the delayed pulse, and I am adding it and doing AND. Similarly, you use NOT gate, take the same pulse, directly you give to AND gate, and with delay you give. Now let us see how it is. Now you see both the pulse, if I make one pulse, one area bigger, you see what is happening. It is giving both the pulse is never coinciding with each other. Got it? If it is coinciding also in a particular position only, it is crossing just for a moment. So my dead time is generated. So you can set your dead time as per that. So what I meant to say, you use in case of multi-level inverter. So just a few days back, one of my research scholar from VIT Vellore, he was working with one multi-level inverter with his topology. So there he needs around I think I can't remember, maybe 12 or 13 pulses or something required. So timer may not be sufficient. So we generated the complementary pulses in this way and successfully able to do with a small chip. So that's why I'm telling, always better to use the complementary pulse externally using some delay, and using this technique you can use FPGA, small FPGA, PL or PLA chip. All these things you can do. There are several techniques to make it practically. Another thing you should know, because we are going to conclude this course, tomorrow will be the last class. There is a thing called power circuit protection. Power circuit protection. Now you see here, here your DC voltage is connected. And here is your load. And you are switching this MOSFET. So when this switch is closed, the load current is flowing through this. Okay? When at once the switch is open, because this is happening in very high frequency, so suddenly that current flow will be zero. So your voltage is equal to V is equal to IR. Okay, V is equal to IR. So if suddenly this current is become zero, what will happen? One voltage surge will appear across the junction. Correct? Suddenly if your current is zero, then R tends to become infinity. So entire voltage, it will suddenly appear, there will be an impulsive voltage across the junction, which is not advisable. So for that, what I am doing, I am connecting one diode and one capacitor in this path, because current will always flow the least resistance path, and the capacitor is getting charged. So what is that size of the capacitor? Say my C is equal to charge by voltage. So this voltage is this voltage, and my charge is equal to current into time. So that is the rated load current of this circuit. Say IL is flowing through this into this. This capacitor should get fully charged T off, till, because as I told, this off is not happening instantaneously. It will take some time to get off. So this is T off by my VDC. So this is the simple calculation of that snubber capacitor. Normally for higher circuit, big circuit, we will use only capacitor, because selection of that, because during the discharging, that capacitor current also will discharge through the switch. So you have to slightly careful that this switch is capable to take the discharging current and the load current. When it will be again switch closed, then the capacitor will get discharged. Okay, so this is my capacitor, this is my rated load current, and this is my capacitor discharge current. So the peak rating of the switch should be at least higher than that. If you can able to do that, then you need not to use that resistance and diode. But if you are not able to do that, so if you can able to do that, only snubber capacitor is sufficient. If you see one of my lecture, I have shown you we have used only snubber capacitor. There is no diode and resistance, because we are well capable to manage that. Now you see, once now the capacitor is fully discharged with the voltage V. Now if you take the Laplace transform of that, now this is plus and this is minus. Now when again the switch is closed, the capacitor will try to discharge, but it will not follow this diode path because it is reverse bias. Then it will take this path to discharge. So this instantaneous current should be given by this VDC by S divided by RS plus 1 by CS. Okay. Now if I know the peak rating of the MOSFET, then this peak rating at least should be equal to my load current plus this IT. So my IT is equal to my IP minus IL, and if you take the Laplace transfer, inverse Laplace transfer of this, you will get a thing in form of e to the power minus something minus t by tau time constant, which is in terms of RS and CS. So CS already we have calculated from the previous equation, and from this equation you will be able to calculate the RS. This is the technique for snubber circuit calculation. Basically it will be used for power circuit protection. Okay, so while it is capacitor should charge very instantaneously, there should not be any resistance path, so that's why it will follow this path. While discharge, the current should get restricted, so that's why while discharging, this diode will be in reverse bias. It will discharge through the resistor, so that the impulsive current you will not get. This is called the power circuit protection, so which are very much used in motor control. So this is the design aspects. So today's lecture is all about this. Now some 2-3 minutes are there. You can ask any question if you have. If you have any question, you can ask. Otherwise, I can conclude the session today. Any question, please? Okay, thank you. So tomorrow we will be learning about BLDC motor control. Thank you so much. Thank you so much. Thank you.